Welcome everybody to this informative presentation that is going to be done by one of our gold members, which is Medhold. The presentation is about technology trends and design considerations. Just a bit of a background about our presenter. We have Chief Engineer for the Surgical C-arm Division of GE Healthcare, David Barker, who is an expert in C-arm design with 29 years of GE Healthcare and OEE medical systems experience. He holds a PhD in mechanical engineering from the University of Utah, as well as numerous patents and peer review publications. David is passionate about sharing his technical expertise with all curious minds. And I think that's why we actually have him today. We will have a QA session a bit later. So we are inviting everyone who's got questions or comments to please post them on the chat box and David will attend to them. So without wasting any time, I will hand over to David to lead us for the presentation. Thanks, David.
So I would like to just kind of give a disclaimer at the beginning. I'd like to discuss some of the trade-offs that we need to consider when you're designing a 3D system to be used as a mobile C-arm for operating rooms. I'm going to try and avoid talking specifically about the products I worked on and would like to really kind of focus on the parameters and the features that you need for an optimal design and why you need them. So we'll try to drop on that, and I'm welcoming any questions that you have. Just kind of be compiling them as we go along, and we'll take them at the end of this. I'm putting this together based on all the work I've done on my own, designing C-arms and also evaluating some of the competition. And listening, especially to the people in the operating room, the pain points that they have and the problems that they need to solve. So let's just go back to the beginning. This is probably a review for a lot of people, but let's just talk about C-arm design 101, as if this is a beginning class. That way we can have some terms and definitions and use a vocabulary that everybody can refer to and have the same words. So naturally, the name C-arm comes from the shape. You have an X-ray source on one side and an X-ray detector on the other side, and they're separated and connected with a C-shaped piece of geometry. That's where it gets its name. And one of the nice things about that is because of its shape, you have a pretty good idea as you articulate the system where it's going to interfere with other things in the room. The shape also comes from the fact that it's rotating about a center point, about an orbiting point. So it orbits about this imaginary point in space and can articulate around. And because of that, and because the motion is more or less an orbiting motion, a lot of times this kind of rotation is called orbital rotation about that center point. And depending on how I articulate the system, if I want to take the system and rotate it over the patient, so I'm kind of making the C into a rainbow over the patient, that direction is called the overscan direction. If I take the C and I want to rotate it under the patient, making a smiley face, we'll call that the underscan direction. And as I add both of those together, that's the full range of motion that you get out of an orbital rotation. That's the orbital range of the system. And for a 3D system, we'll be getting into what you need to have an effective design, if that's what you're trying to accomplish. And in this position I've shown on the screen, a lot of times we'll call this the 0-0 position or the home position. A lot of times because of the way the anatomy is oriented, anterior, posterior, a lot of people will just call this the AP position because the patient's pretty much going to be right there in the beam, in the C in this orientation. Now, for most C-arm designs that are out there today, the image chain, in other words, the X-ray tube and the detector, the center line between the two, doesn't go through this imaginary rotation point. It's in a different location. So the image center can be going through the center point. If it goes through that rotation center, we call that an isocentric design. If it doesn't, we call it an offset design. And obviously, as this offset gets bigger, It makes it a little bit more challenging as you try to articulate the system and keep the image relatively centered where you had it last time, because the offset will start throwing things off. But we'll talk about why people like an offset in the system. And it turns out for a two-dimensional system, if you're trying to optimize for a two-dimensional geometry, having an offset actually can be a benefit. For a 3D system, it produces some real challenges, but we'll talk about that some more. One term that people use a lot, you probably have heard this term, is the source to image distance. That's measuring the starting point on the generator, the focal spot on the X-ray tube, to where the image starts on the scintillator on the detector. That's the SID is a big measurement everybody likes to talk about. The thing that's kind of interesting is that you practically have no good way of measuring this. You have to kind of trust the people who manufacture to understand what that is, because all the things that you really need to measure are under covers. The focal spot is obviously inside the X-ray tube, underneath the collimator cover, and the scintillator is inside the detector, which is underneath the cover inside the detector housing. So although it's a really common word that everybody likes to use, it's really impractical for people to try to go out and pretend to measure it. As the SID gets bigger, because of the way X-rays work, I have to increase the power at the X-ray source to get the same dose to hit the detector, because this is changing with the square of the distance. So the larger the SID, the more energy I have to produce, again, to get the same dose that I would get with a smaller SID. There's some different design trade-offs you can go through in doing that, but obviously there's going to be design considerations depending on what you really want the C to do, and how big of a patient, and how kind of on the clearance that you're looking at. So the SID is a key factor for that. And of course, you need to slide the whole C over the patient, who's typically on a table. So measuring where's the detector cover to the collimator cover is called the free space. And that just lets you know how much margin you have as you're working with different size patients and different size tables to try to get the C placed in the right spot. This is a term that I've used. It's kind of one I've come up with on my own. You won't find this probably published in anybody's work. You won't find it in anybody's technical data sheet. But this center to image distance, in other words, where's this imaginary center plane distance to the detector surface, turns out to be a real critical parameter in determining the workflow and the usability of the C for 2D and 3D applications. If the CID is too big, it usually means that the workflow for the staff is going to be interrupted constantly by changing the height of the system, or moving the table, or doing something because you just can't get the image projected onto the detector the right way. And if it's very small, you minimize your magnification on the detector, but if you make it too small, then there's no room for the doctor to operate in between the detector and the patient. So it's really kind of a critical measurement in understanding how easy the system is going to move and articulate around the patient, and make it easy for the staff to use the system. But it's one of these parameters that you won't find. So we'll talk about it a little bit, and we'll talk about some other ways you can detail if the CID is a good number with some other parameters that are out there. Another one you'll hear is the depth of arc. This is not the center point to the inside radius. This is actually where's the image chain center to the inside radius of the C arc. So that'll include the offset and the radius of the system. On an isocentric system, it is really just pretty much the measure of the inside radius, but the true definition is where's the image center to the inside of the arc. It turns out people like to talk about this term a lot. It really has very little influence on a good or bad system. It's an interesting number, but as far as clearing the patient, unless you're doing special procedures where you need to slide the C in to get to the anatomy, maybe kind of showing this way, or you will find a certain set of surgeons, vascular surgeons, want this number to be semi-infinite. They don't articulate like other surgeons, and all they really want to do is scan the patient in all possible ways. without doing a whole lot of articulation. They don't really even need a C shape. So I will just let you know, although you can look at this on spec sheets, the depth of arc is really a parameter that people track, but it really doesn't influence a great design one way or the other. This parameter, the percent field of view, is a really important parameter in understanding the differences between good, an excellent, medium, or terrible 3D systems. What this is actually measuring, as you take the exposure and you project it from the source to the detector, the plane where it crosses the rotation center is going to give you a fraction of the full image size. So if the full image size is 100% at the detector, as I come down to where I hit the rotation plane, that's going to be the important plane for generating images, the way we're going to do it on a 3D system. So knowing this percentage is a really big indicator of how big your 3D volume will be, or how small your 3D volume will be. And it'll also give you an indication of other aspects of the system of how usable it will be. So we'll talk a lot about that a little bit later, but I'm just introducing that. So the percent field of view is a really important parameter in C-arm design. Okay, so now we have a whole bunch of different parameters, and we need to figure out, well, what's the priority? What's the important parameter for the design of the system that I need? Well, to decide that, you kind of have to decide, what problem are you trying to solve? What's the primary purpose of a surgery center? What is the problem the hospital is trying to solve? I'm going to propose that this is what they're trying to solve. They're trying to generate the greatest number of positive patient outcomes. That's their business. A positive patient outcome would represent a successful surgery where the problem and the complication has been mitigated. It's allowing the patient to heal as fast as possible. Infections are non-existent, or the chance and the risk of infection has been reduced as much as possible. And the staff is able to service the maximum number of patients in a given day. That allows the hospital to have the best business model. They have the best success rate. People refer other people to that hospital because of these good outcomes. So what's the main contributor to meeting this goal? If you're trying to get the best outcomes in as many as possible? Well, it's going to be the surgeon. As far as outcomes are concerned, the surgeon is responsible for all the outcomes. The surgeon is the ruler supreme in the room. Everybody is subservient to the surgeon. The surgeon is making all the calls. It has the legal responsibility for what happens in the room, and is ultimately the last word. You'll see this picture. You can identify the surgeon. The surgeon's the one looking at the screen, probably at this point, either working with the catheter or some contrast with the patient. And you also notice that the C-arm is independent of the surgeon. This is kind of an interesting analogy. I'd like to try to say that, to me, as you design the best system for the surgeon, it's as if you're trying to design a really nice car for a rich person who's going to buy the car and sit in the back seat and have a chauffeur drive the whole time. They'll never even start the car, drive the car, stop the car, or anything else. They'll just be in the back and they'll tell you, hey, I like the car, I like the ride. So designing a car for someone who never drives the car is a real challenge. So designing a C-arm for a surgeon who never really uses the C-arm poses some interesting problems. Because what we're trying to do is optimize the workflow for the surgeon so that they can have the best possible outcomes and have everything run as smoothly as possible. But yet the device that we're talking about is really never going to be used typically by the surgeon. It'll be used by other members of the staff. So to understand how we can improve the surgeon's workflow so that they can get the best outcomes, let's talk a little bit about how the surgeon works and what's top of mind for the surgeon. So one other word that you'll probably hear is MIS, or minimally invasive surgery. By definition, a surgeon is someone who impacts the human body in their operations, typically by cutting something. And in the olden days, they would open up the patient to see what they needed to see. And the incisions could be very large, so they could explore, move, cut, suture, do whatever they needed to do. But over time, they've realized that if there's some other way they can see inside the human body, then the number of openings that they need to make can be minimized, and even the cuts they need to make inside the body can also be minimized. So that's where the whole idea of minimally invasive surgery comes from. The advantage to the staff is it goes faster. It takes less time to operate on a patient. The patient has less openings. There's less risk of infection. They will heal faster. The outcomes tend to always be better for a minimally invasive surgery operation than they are for an open surgery. So this is definitely something that's going to help with improving the patient outcomes with reducing all these other risks. So taking that in mind, realizing that the big task of the surgeon is to see what they need to see. Let's talk about optimizing their workflow. I propose that there's really three things that you're trying to do to help the surgeon. You want to give them the best images possible at the lowest possible exposure to the staff and allow for the highest amount of throughput in the room. In other words, being able to do the procedures as fast as possible with the minimum amount of errors. So IQ, dose, and throughput would be the three big players, and anything we can do that impacts those in the design of the C-arm are going to improve the surgeon's workflow, which then in turn would help with all the positive outcomes. So with that said, let's talk about 2D imaging and why is 2D imaging such a big deal in the surgery area, and why would we even want to be talking about it now, since this whole presentation is supposed to be on 3D C-arms? Well, I'm going to tell you a quick story. Back in the late 1800s, France was at war, and they had hired a mathematician who was working on a top secret project, trying to figure out the best way to communicate how masonry stones could be designed for fortifications. And this Frenchman came up with this great simple idea that almost any of these objects could be explained by two simple pictures that were 90 degrees from one another. This was top secret information. As soon as the war ended, everybody stole this idea because it was such a great little idea. But in the past, what happened was a master stonemason would have to show a journeyman by hand as an example, make it like this, and would constantly be overseeing the work. This freed up everybody so that everybody had a very simple plan, and with two pictures at 90 degrees from one another, knew what to make, and it improved the throughput for all this. He called this orthographic projection. In other words, the two pictures are orthogonal to one another. Once the war was over, this idea spread all over the world, and soon engineering especially took hold of this, where you could describe almost any part you were trying to describe with two simple views, and what would allow the person looking at the picture to take these two pictures, and in their head, they would then build a three-dimensional picture just based on these two simple two-dimensional projections. And orthographic projection is still used today in the major ways of documenting most engineering parts. And it allows people to build a 3D picture in their head from the clues that you leave them. Not long after this, there was another Frenchman in 1900 realized that they could characterize people's identity by taking two orthogonal photographs. We call these mugshots today. And this is also a Frenchman who came up with this not many years after the whole idea of orthographic projection was floating around. And with this, again, the idea is from these two clues, you build a three-dimensional picture of someone's face, and you would be able to identify them just by these two simple images. So now we take this and we go into the operating room. And if we take two images, X-ray images at 90 degrees, this allows the doctor to build a three-dimensional model in their head of what they're looking at. And just by taking two shots, which take very little time, orienting things at 90 degrees, they're able to get these two shots, build a three-dimensional picture, and make a decision. And what they're doing is they're doing a poor man's three-dimensional map in their head with just these two shots. So for the workflow to work, to optimize the throughput, what you need to do is allow the doctor to quickly get the two images that they want as fast as possible. This sometimes will happen by the way they orient the patient, and then you're just taking the C-arm and you're going in 2 90-degree positions, grabbing a few images. Now, even though 3D images add more information, the doctors typically still go back to a couple key 2-dimensional shots for communication and also for quick documentation purposes. So today, there is no doctor who relies 100% on 3D images and never, ever goes back to 2D images. They all require 2D images to get their work done. So that's an important thing to remember. Although we're talking about 3D, no doctor is going to walk away from all the simplicity and quick throughput that they can get by these 2 key shots. They might take more, but they're always going to rely on 2D images for documentation and for their procedures. So, and why do we need 3D images? What does a 3D image give you that you can't get from building this model in your head from the 2D images? Well, let's just go for a minute and discuss how our 3D image is constructed. They're actually made by gathering a whole bunch of 2-dimensional images. So the traditional way this is done is by projecting and exposing small strips of the image, almost like the strips you'd get when you put something on a copier, and it just scans little strips at a time, and then finally compiles your full 2-dimensional image that way. But they'll do this in an arc and spin around and gather these, and then they'll move down on the axis of the patient and create another set and another set and another set, and they'll compile those together to make a 3-dimensional volume. What typically happens on a C-arm is, instead of having a strip, you use the exposure, which you're getting from a C-arm, which is a point source spreading out in a prism or in a cone, and then hitting your detector, and they'll spin that around and gather enough images that they can then interpolate between those images to calculate what the 3-dimensional volume should look like if I've gathered enough. Now, for this to work, for cone beam CT, what you need is at least 180 degrees of travel plus the width of the detector in order to get all the geometry that you're going to need to fully define the 3-dimensional volume. And if I can get more than that, then I start to minimize the chance of artifacts coming into the calculations. So for most systems, the 180 degrees plus the width of the detector is going to require that you need about 194 to 198 degrees of travel. More travel is better, but you pretty much need 196 is a good number to think about as the minimum amount of travel if you're going to have a C-arm be used to gather all the images that you need for a cone beam CT. I want to show this picture for a couple reasons. This was obviously made over 10,000 years ago, and it's probably one of the first ideas of a cone beam projection. It's done with paint, obviously, instead of photons, but it's creating a shadow graft of people's anatomy and putting it on a cave wall. And it's really kind of an interesting thought to think that, over 10,000 years ago, somebody was thinking of a cone beam projection system to try to identify and quantify anatomy. The other reason I needed to show this picture is this was done by somebody in France 10,000 years ago. So again, the French just seem to be part of this process a lot. Okay, so if we talk about 3D imaging, once we have the 3D volume, people typically break it up into 3 orthogonal planes. The planes that you're used to seeing in the 2-dimensional world would be called the sagittal or coronal planes. They'll be slicing down the patient this way, the kind that you could get a 2D image pretty easily with your C-arm, and you could be taking our loaf of bread and slicing it lengthwise, either one way or the other. The magic and the wonderful thing that you get out of a 3D image that you don't get from the 2D is this axial shot, where I can actually see a slice at a time going from top to bottom, from the head to toe of the patient. And that axial shot is really magical and gives so much more information that you just can't get from a 2D when you need it. So let's go back again. I have these 2 orthogonal views, my very good 2D views, again, giving me a good way to start having my brain build a 3-dimensional picture of the skull and neck But one thing I have a hard time doing with just these two pictures is knowing exactly how far the screws went into the neck. But if I can take a 3D image, okay, and you can see on the right-hand side, I pretty much have my coronal and sagittal views shown on the right-hand side. But this axial view now, where I can slice right down the neck and say, what am I seeing right at this plane? I can see exactly how far the screws are into the bone, making sure I'm missing anything that I didn't want to impact, and that the placement is exactly where I want it. This is the magic that 3D gives you that makes the problem really clear. And there are certain situations where you can only accomplish this with a 3D image. And it's just going to be too hard to take enough 2D images and let the doctor figure this out any other way. So now let's talk about the design. So if we're going to try and balance the design so that we get what we want, what are the variables that really help us come up with an optimal 3D system? Well, I'm going to have to talk about a couple more variables that we didn't talk about before. We just talked about the shape of the C, but there's other things that go into the design of the system. One of the first ones we need to talk about is the lateral height. Now, the lateral height is, I'll take the C, I'll put it in an underscan so that the image chain is parallel to the floor, and I'll make the system go as low as possible. That's what people will call the lateral height of the system. Now, this is also kind of defining the lowest possible location that you can reasonably use the C in operation. Since there's a lot of people out there that aren't as tall as other people, this is a big parameter that drives the usefulness of the system, especially for a doctor that's not very tall. The only other recourse you have if you don't have a system with low enough lateral height is you're forcing the doctor to step on a stool, which now limits their mobility in the room, also kind of introduces some safety issues and makes it a real challenge. There's a lot of studies on the ergonomics and the problems of trying to do this, and how the doctor's position minimizes the usefulness of the system if they don't have their neck in the right spot, their eyes aren't looking the right way, if their elbows aren't in the right location. Now, that's not to say that everybody in the room can get away with having a lateral height and making everybody happy, because everybody's different heights. But certainly, if you're trying to get the best outcomes, you don't want a system that's going to compromise the doctor by saying, sorry, this is what you have to do. You really want it to be under the doctor's control to say, the system is where I want it to operate on this patient, and I can get it at the height I want. Now, there's a trade-off with that. The lateral height is going to be pretty much defined by the radius of the C and the offset. And the bigger I make that, the bigger the lateral height is going to be, because the whole system can be off the floor. So if I shrink the C, I can get the lateral height down. If I got rid of the offset, I can get the lateral height down. But then, well, what's the right size C? When's the C going to be too small to be useful? Because again, I have to have the free space to get in. And when's it going to be deep enough for me to do what I want so I can get around a fat patient on a table? So there's a trade-off there as you're working through that. Now, the range of motion of the C also plays into this, and there's going to be a trade-off between, well, how much free space do I get as I make the C bigger and as I make the C smaller, but also if I'm going to have a certain projection limit away that the C is going to travel. So let's imagine I had the detector sitting at a certain distance away from the center point of rotation. I can't probably expect the C to go too much further than that and be useful. Otherwise, the C is now going to be in the doctor's way, even more than the detector is. So there's some magical X dimension that I don't want to violate. And I'm going to have to look at a trade-off between those two to try to find the best size. Now, the weight of the system is also going to be changing. The weight of the C and the stiffness of the C is going to change depending on how big I make it. As I make a C big, as you all know, a longer diving board bounces more than a shorter diving board. That's if I make the C of the same material. So if I want to make the C stiffer, I'm going to have to make it thicker, which is then going to influence its weight. And the weight of the C, because of its shape, is never going to be at the center of rotation. It's always going to be back away from that. And for a good design, I'm going to need to balance that with the weight of the detector and the weight of the X-ray source generator. And ideally, especially if the system is going to be ever used in a manual operation, I want all those weights to be added up and centered at the center of rotation. If I can do that, it makes the C very easy to move. If I can do that even for a motorized system, it makes the speed very consistent. And as I'm trying to reproduce three-dimensional motion, the more I can get that exact and balanced, the more consistent I can allow the generation to happen and minimize all kinds of other artifacts that would be happening as I spin the system. So I really, it's to my advantage to try to get everything to balance at the center of the C. Now, one thing you find, regardless of who's designing the C, whatever manufacturer it is, the C is extending far away from the rest of the system. It's a big piece of geometry, and no matter what you make the mass of that whole system with the X-ray tube and the detector, that mass is projected so far away from the rest of the system that I need to typically add 3 times the weight of that entire assembly to keep it from tipping over. So it's a lot like a teeter-totter problem with 2 little kids. You have one kid who is using the fulcrum to their advantage, and they can keep this other person suspended in the air, even if this other person weighs a lot more than they do, just because of the mechanical advantage. We have the reverse problem for a C design. We really need to get the whole weight of the C and the source and the detector as small as we possibly can to keep the weight of the system down. So whatever the weight of the C is and its components, the system weight is going to be pretty much 4 times that. So a good design is going to try to do everything it can to minimize the weight extended out on that cantilevered load. One of the big sources of that is going to be the X-ray tube. Now you have a monoblock where the generator is right next to the X-ray source. This makes for very small cables because I'm taking low voltage and I'm turning everything into a high voltage locally. However, it makes that device very, very heavy because I put both masses on the C and I'm balancing them out and I've cantilevered everything out. So the weight of the whole system is going to go up a lot when I use a monoblock. And the solution to that is you go to a split block where the X-ray tube is obviously out at the end of the C, but the generator is far and remote and maybe even part of the counterbalance system further away. So it makes the whole system much lighter. The trade-off is you have fatter cables going between this high voltage tank and the X-ray tube, but the whole system weight goes down quite a bit. So that if you're trying to keep the system weight down and keeping it mobile, so it's a mobile product and easy to move around, then this is one of the key things you'd want to look for in a good design. Now, we talk about the system being mobile, and the system weight is a variable that you've got to look at to say, well, how mobile is the system? The fact that it has wheels means nothing. Pianos have wheels and nobody moves the pianos with the wheels. They always take off the wheels, put it on something else and move it around because it's just too heavy. The same thing happens with the C-arm. As the C-arm weight gets heavier and heavier, although someone says, well, look, it's on wheels, it's mobile. If the C-arm is really that heavy, it's really not going to be mobile. The throughput, the workflow in the OR is going to be compromised because it takes either one person or now you have to motorize the whole system just to move it around in the room. That's not going to be optimal. So for a good workflow, you want the whole system weight to go down. Let's talk a little bit about what happens if we took a normal 2-dimensional system with an offset and tried to use it to generate a 3-dimensional volume. What do we get? So typically a 2-dimensional system without any extra work is probably going to give about 145 degrees of travel. And with the offset, you can see in this one, it turns out that for this situation, the field of view that you're using to spin about the center rotation never overlaps with itself. So I never really get enough geometry overlapping to generate a good 3D volume. So the offset allows me to make it a whole lot easier to balance the C and to get the whole weight of the C assembly lower, which then gets the system weight down, but it gives me absolute terrible 3D coverage. So really to get good 3D coverage, you need some way of keeping the center of the image about the center of rotation all the time. Practically, the best way to do that is to make the C isocentric, but you could do something where you're constantly moving things to keep the center of the image in that center rotation plane so that I can get full coverage. Now, if you do it isocentrically, it does make the system a little harder to balance, but it does give you the full coverage. So an optimal design would really be an isocentric system to give you that. Now, the detector is also going to determine something about the usefulness of the images that you're getting. There's two big technologies out there, are CMOS technology and amorphous silicon technology. You can kind of see some representations of what happens when you actually have a silicon crystalline structure that you have in CMOS versus an amorphous silicon structure that you're going to get in amorphous silicon. The difference is that the silicon structure in CMOS is well over 1,000 times faster in electron mobility. That huge difference in speed allows me to do a lot of things with CMOS I could never do with amorphous silicon. So one thing that happens is if I want to get a full resolution and I want to get it 30 times a second to project and see what I want to see, I really can't do that with amorphous silicon once the pixel size grows too big. The only thing I can do at that point is I then have to start averaging neighboring pixels. This is called binning. So I'd take maybe 4 pixels and average them to one big fat pixel, and then I can show that 30 times a second, but I'm getting a lower resolution. So you can kind of see the second row with the 5 and the S, that sometimes depending on the orientation, because you got fatter pixels, it's a little bit harder to discern what's really going on. Or I could just say, I will go with full resolution, but I'm only going to go every 15 times instead of 30 times. And you're going to be throwing away a little bit of information that way. So again, the best design would be using CMOS. It has less noise. We could have a whole presentation on the difference between the two, but just keep that in your head. You'd like CMOS over amorphous silicon. The other thing that's ironic is people will talk about the wonderful resolution they have on their detector. They'll talk about all the wonderful things they're doing with their processing and how well they're calculating everything. And then they send it to a really low resolution monitor, which is doing the same thing as binning again. They're taking all this wonderful calculations and they're saying, well, I'm not going to show you all my calculations. I'm going to bin my calculations and send it to a really dumb display and throw away all this great calculation. So I'm showing you fat pixels at the end of the problem instead of gathering fat pixels at the beginning of the problem. So with the technologies that are out there, it really, you're doing yourself a disservice if you're not going with the 4K display with all the calculations and all the resolutions that everybody has on the detector. You really want a 4K or better to give you full resolution on the output side of the problem rather than just worrying about the input side. I won't talk too much about this, but the X-ray source itself, to really give you the throughput that you need, it turns out for a 3-dimensional imaging problem, heat is really not a challenge. Heat is really not a challenge in 3D imaging. Heat is the problem in 2D imaging, especially when you're doing cardiac work and other things like that. And the way people typically solve the heat problem is to go to a rotating anode. Now, the rotating anode is going to make the whole system a little bit heavier, but it's going to give you more options with handling the heat. And as we're worried about trying to give the best X-ray image we can at the lowest possible dose and the highest throughput, we need to realize we can't touch one of those without touching another. So you want to also be careful about just looking at resolution or just looking at the power on the system or whatever, because as I increase the dose, I can obviously get the image quality to go up, but then my throughput's going to go down. I'm going to overheat my X-ray tube quicker. Or if I try to starve it, then my image quality is going to go down, but my throughput will go up. But is the image quality where I want it to be? So let's think for a second about this. You could also always look at a bigger generator as something that's a nice variable. But if you think about what you're doing on your phones today, is we're all taking pictures with our phones. We have all this great technology. We can either play with some games and manually adjust this poor image that I took in bad lighting and have it enhance itself, or I can even have some software that'll just kind of fix it like a Photoshop or Adobe. There's a lot of different things out there that'll do some great noise reduction and allow you to starve the image, keep the dose down, and yet still produce a good image at even lower power. So you're increasing your throughput. You're still getting the image that you want. You don't necessarily need to invest in a bigger generator, and the image is still meeting all the needs. So you probably want to look for systems that are using some good noise reduction technologies that are out there, rather than just say, we're going to do this the old way and we're going to just crank up the dose to get the image where we want it to be. As we're still talking about heat management, you want to look at the difference between the energy and the rate. Now, I've got a picture of 4 different things here. These all account for 200 calories. But your body is going to burn each one of these 4 things in a different way. It's going to burn the butter much differently than it's going to burn the celery. It's going to burn the apples much different than it's going to burn the gummy bears. As people talk about heat, again, for 3D, heat is not a big deal. Heat is never a limiting factor in the design. Heat is the big issue for a two-dimensional system, not a three-dimensional system. But as you look for different factors, look at the rate it will cool off. How fast can it cool off? Don't just look at the heat capacity. That's not a good measure. You want to see how fast can it cool off? How long can I use this system before it overheats? That's what you really want to find out. Okay, now we got to jump into one last thing as we're balancing everything out. As I think about a three-dimensional system, I need to spin it around a patient. So I need to make sure that it clears the table, clears the patient, and we call this clearance the bore size. How big is the bore? On a typical traditional CT system, the bore size will be called out, and it'll be the tube that you're going to slide everything through. The table's automatically part of the system. In our case, it's not. So we kind of have to find where the table is, spin around it on a mobile system. And these 4 variables are going to be key in determining how good of a design you're going to get. So the CID, again, what's the distance from the center to the detector? What's the SID, the source to the detector? How big is the detector itself? And then what's my field of view going to be when I spin it? So as I change the CID and the SID, I'm going to get different combinations of a field of view, and I'll get a different reconstruction volume. And if I think about the CID and I just multiply by 2, that's pretty much going to be my bore size. So all the things that I really want are going to be pretty much captured with these 4 things. And it's going to tell me if I'm going to get a system that I want or a system that's optimized one way or the other. So if we think about these variables, and I have a typical 2D system, and I look at what would happen if I designed it specifically for 2-dimensional use and made it as good as possible for that, my field of view is probably going to be 67 to 70%, which is going to be this wonderful big volume. But my CID is really limiting my bore size. So my bore size is going to be probably too small to get around most people. It's going to be less than what I get in a traditional CT system if I had an FOV percentage that big. So it'd be great for 2D, but not very good for 3D. Now there is kind of a magic spot. If I can get the FOV about between 60 and 64%, I still can have a system that can be used in 2D easily and 3D, and gives me great 3D, gives me a good bore size. This would still probably give me a bore size in the 70 centimeter range and give me good workflow. And I can have one system in the room now that does both, instead of needing to devote my money to build one 3D system and then buy another 2D system. Because again, the doctor needs 2D and 3D in the room at the same time. So I either going to use more floor space for 2 devices, or I could kind of design one which will do both things at the same time effectively. This is kind of the magic you're going to want to find. Get an FOV between 60 and 64%. That's going to tell you the CIDs where you want, the SIDs where you want, the volumes where you want, so forth, and the bore size is going to be where you want. Now, as I start going bigger, yes, I can say I have a bigger bore size than someone else, but now my reconstruction size is going to be smaller. I'm down at 50% now, or closer to 50%. Yes, I have a bigger bore, but I'm gonna have a smaller reconstruction size, and I'm starting to make my CAD so big that now for 2D, this is not as useful as a system. I have to start using all kinds of other features on the system to get what I want. And then of course, if I make it bigger than that, it's not adding anything to anybody. It just says I have a bigger bore size, but it's not really as useful. Okay. Now here's what's the difference between this ideal 2D, 3D system that's going to give me a bigger field of view of 63% versus a standard one, which is going to be a little bit in the low 50s. I get to see a whole vertebrae more for a system which is at 63% than I am at 53%. So there's a lot of them out there that'll be in the low 50s, and but the optimal design is going to be around 63, 62 to 64, and you're going to be able to see a whole additional vertebrae in your reconstruction size, and you still haven't sacrificed that much with your bore size. So a quick summary of the parameters that I think are the key parameters to a good 2D/3D system. So the system's doing everything you want. Is you want to get the 3D FOV, something that's going to give you a reconstruction volume of 18 centimeters or bigger. and that's going to allow you to see about 5 vertebrae. That will give you the 3D bore size of about 70 centimeters or bigger. So if the CID is about 38 centimeters or smaller, that's if you actually could go find that number. Those 3 things kind of work in concert. Okay. Again, the orbital range you're going to want, it has to be at least 196 degrees. More is always going to be better. A lateral height for most people in the world needs to be about 1 meter. If you can get it lower, that would even be better. It's pretty hard to get the whole system to do anything lower than that. And as it gets higher than that, it starts to be a compromise for the workflow in the room. For it to be a truly mobile system, if you're pretending that you really can push it around, the system needs to be about 350 kilograms or less to really be truly mobile. As it starts to get heavier than that, it doesn't matter what wheels you've got on it. It's just hard to push on the floor. And it makes it less easy to really be called a nice mobile system. And if you're really interested in the 2-dimensional problem of cooling rate, look for something that's going to give you 500 watts. Now remember, watts is the rate of cooling. Don't worry about the heat capacity. Don't worry about all those other things. Find something that's got about a 500 watt cooling capacity, and that'll help you if you've got cardiac and vascular work that you're doing in addition to your 3D. Now, I've talked about mainly to the geometry, talked about mainly things that are related to mechanical trade-offs, and I'm completely out of time. And if I had more time, we would talk about all the wonderful things that need to go into designing all the software that makes the system something that the doctor says, wow, this is amazing. But I'm out of time, so I'm going to have to stop. So I'll open it up for questions.
Thanks, Dr. David Barker. I'm pretty sure what we have done is to actually make me very clever when I go and discuss this with the clinicians, if for any interest of C-arms in the market. But thank you very much for the information. It's much appreciated.
Sure.
I see on our chat box, we don't have any questions. Take it that is a sign that the information was clear and also very informative. But I would like to mention that through the acceptance of Medhold and also GE, they have allowed us to record this session and also to publicize it into our web platforms. So I think in a day or two, we will look at this the presentation and publicize it over there. And if you have any questions or comments, I think feel free to contact your nearest Medhold or GE branch to get some clarity going forward. Yeah, I think since there is no questions, I will maybe close the session. And thank you again, Dr. Barker, for your inputs and also sharing the experiences, and to Medhold and also to GE. And we're looking forward to hear some information sharing again in the near future. Thank you very much.
Okay.